Welcome to this demonstration of Beyond Security's beSTORM. Today we'll cover a simple review of beSTORM's fuzzing capabilities inside of web applications and web servers. To begin, plug in your protected USB key dongle and launch your beSTORM client. From here, you can select to load an existing project or load or create a new project. beSTORM is designed to an enterprise-grade black box fuzzer that requires no access to source code or proprietary data in order to generate valuable test results that can help development teams locate and mitigate zero-day vulnerabilities and other critical issues. beSTORM is capable of assailing a multitude of protocols, as well as file-type fuzzing and various other custom modules and functionalities. beSTORM covers a broad area of modules and protocols from default, including things like DNP3, DHCP, FTP, HTTP, SMTP, SNMP, SSL, DNS, EtherCAT, FTP, HDCP, and more. The list of built-in modules is fairly extensive and covers anything from high-level to low-level network protocols, as well as file-type protocols, including major multimedia protocols as well as ISA, EDSA certified components that allow organizations to self-certify in the EDSA standard for a variety of communication protocols. We also cover wireless, Bluetooth, and Wi-Fi stacks, serial stacks, and custom implementations such as CAN bus and J1939-21. For this demo, we will use our simple HTTP web client fuzzing engine. beSTORM also comes built in with the capability of building custom modules from its ability to execute man-in-the-middle, HTTP proxy, or network sniffer capabilities. beSTORM can also digest and automatically generate fuzzing modules based on files from the file module system, as well as build custom modules straight from an XML editor. It also has the ability to use DLL or API modules, or build custom web application and ActiveX modules based on crawled web applications and executed ActiveX modules. Using our HTTP module, we will instruct beSTORM to look for a web server at a specific address, and for that, I will launch a simple web server application on my local host. This web server is listening for connections incoming on port 80. To verify that, I will simply fire up my web browser and point it to my local host on port 80. You see here, we're getting a response code 200, verifying that the server is running and responding correctly. We'll now instruct beSTORM to attach to that target to test using the TCP protocol on port 80. Now we'll hit Next. This takes us to some advanced configurations for the module. Some modules carry more advanced configurations than others, and these configurations allow us to more tightly define the fuzzing parameters that we would like to execute in this particular test. This includes things like assigning valid values to specific fields, or assigning strictly invalid values to other fields that will remain static. Click Next. There are some additional configuration options. Saturation rate, indicating the number of fuzzing engines that are executed per attack iteration, the type of monitor used, and whether or not we should use an external monitor. Since we are attacking a Windows-based web server here, we will launch and execute our beSTORM monitor inside Windows. Our monitoring systems are designed to accurately track and debug the application when a stack area is hit based on the testing done by beSTORM. In this case, I will instruct my monitor to attach itself to my simple web server. And now, we'll instruct the monitor to look for beSTORM at a specific address. In this case, we are running on localhost, and I will simply attach the system and enable persistent monitoring in Watchdog, which automatically relaunches the process when a fault is encountered, so the testing can continue without any interaction from the user. beSTORM Monitor also allows you to monitor things such as services or explicit TCP connections. We also have a series of other available monitors built into Linux NICs, FreeBSD, AIX, and hardware monitors, which allow you to deploy and execute the most relevant monitoring scheme required by your test case. This allows us to monitor anything from hardware appliances to software stacks, servers, and clusters. In this case, as we're using an external monitor, I'm going to instruct my system to look for this external monitor on the local host, which is currently attached. Now we'll hit Next. And with those few settings, we have now set up our baseline fuzzing session, which is ready to execute whenever necessary. Here we have a module browser, which lets us know that we will be covering about 15,000 attack combinations. and each attack combination has a permutation of a couple 100,000 attack vectors per combination, meaning that this number of attack combinations grows exponentially as the fuzzing engine builds its way through the attack parameter. We are able to browse through the module and see what specific components of our packets are going to be fuzzed. For example, here we will be fuzzing the URI, the HTTP type, HTTP major and minor, host value, user value, and other parameters. Now let's execute the fuzzing by clicking Start. As you can see, our web server is receiving these requests and discarding them or responding to them as it sees fit. And this fuzzing will continue unattended as long as necessary until a fault or crash is detected. Our monitoring system will monitor the process and attempt to gather as much debug data as possible in order to build a more comprehensive report to see exactly what failed inside the software component on your test and what attack vector used by your fuzzing engine caused the issue. Fuzzing sessions can be as short as minutes or as long as weeks, but the longer the fuzzing engine executes through the stack, the more likely it is to detect vulnerabilities hidden within the code or the application or the protocol being tested. As we can see, we have now hit our first vulnerability. The system allows you to automatically relaunch applications and remonitor them so that beSTORM can automatically resume testing. Our system automatically resumes testing to continue building a comprehensive list of possible vulnerabilities in the system. I will let this run for a few minutes to gather as much test data as possible. Another exception has been caught, and the system continues to scan. In the span of about 6 minutes and 30 seconds, we have detected 5 possible vulnerabilities. Let's pause testing, rearrange our windows. Let's detach our monitor, shut down our monitor, and let's view a report of detected vulnerabilities. We located 5 possible issues inside of my software during the test. This includes a process terminating unexpectedly with a proper error code and a stack trace detected by the beSTORM monitor. Also, it lets us know the test type, the value here, an unsigned character, and the specific attack vector used by beSTORM, and the specific packet sent over to our server that caused the crash in question. We're able to browse through our findings. See here we have a page fault, another page fault terminating unexpectedly, and a page fault on write access. From this screen, we also have the ability to export. Exporting allows us to automatically build a proof-of-concept attack script, which can demonstrate a reproducible attack based on the suspected vulnerability. I will export 2 samples, and I can shut this window down and save my project. I can also generate an HTML report, which will review specifics of this test case, specific settings used under this test, specific environment settings, monitor settings, ports, the attack types used, as well as the running time between possible vulnerabilities detected. So we can see here it took 33 seconds and 2,982 combinations before the first exception was caught. Subsequently, 2 seconds and the next attack combination yielded our next crash, and so on. The report also gives us a list of total exceptions. Again, the information regarding the possible crash type, the stack trace, the attack vector used by beSTORM, and the data that was used to generate the exception. This report can be formatted in HTML, PDF, XML, or any other format required. I will now shut down beSTORM and show you the proof attack concept script that is automatically built by the beSTORM engine. See here we have our Perl scripts that were exported earlier. As you can see here, it is an automatically built script which exploits the possible vulnerability detected by sending the specific crafted packet that caused the crash in my web application server. To test this, I will simply copy my files over to my root folder, and I will execute a portable Perl shell. I will also bring up my web application server. And to verify that the server is still working, I will launch my web browser and log into the local host. As you can see, the server is still responding appropriately with a code of 200, and the log reflects the same. Let's now execute our Perl script, pointing our Perl shell, and execute. As you can see here, the web server has now crashed. With a failure in BC runtime, an exception code, and additional information, it was automatically captured by the monitor in our previous iteration. I will relaunch my web server, relaunch my browser to verify the server is working appropriately. And as you can see, the server is responding. Let's re-execute our script And as you can see here, we have a reproducible crash, and we have now weaponized our detected suspected vulnerability automatically using the beSTORM engine in a simple fuzzing session. We can also execute the second script, so we can see it's responding appropriately with a request code 200. Then if we execute the shell, we see that the server still crashes. Now Perl script file 2 seems to be having a harder time actually causing an exception in the server, and of course this allows us to debug the information a little more and determine if there are specific environmental variables that are required before the specific packet can cause a crash inside the host. All that information is of course automatically generated by the beSTORM engine, and this allows beSTORM to become an integral part of your developer process and allows you to detect any zero-day vulnerabilities and address them long before release or during release, before they are publicly disclosed and discovered by third parties. Thank you very much for joining us for this brief demonstration of beSTORM, and if you have any further questions, feel free to contact us.